So, good morning, everyone. So, I'm back again. So, today I'm gonna talk about the same topic but in English. So, my previous video was in Punjabi, in my home mother tongue. But today I decided to put the same presentation in English. Um, so, I have discussed this presentation couple of times, like in different universities and colleges, but I would like to put it in the YouTube as well so that anyone can see. So who can be the audience? The audience can be anyone who is like aspirant, who is a physicist, physics physics aspirant, and who is new in the research, like especially for nuclear astrophysics research. They can see this video, but this presentation will be very general so that any common people can understand, right? Any layman can understand, they can relate to their understanding of physics. But at the same time, as I said before, it would be also helpful for the students, like first year PhD students or MSc students, so they can better understand, they can better relate with the physics that they know already from their previous classes, and how they are going to apply to the physics they will have to do in the research, right? So in this presentation I'm not going to talk about any, you know I'm not going to show any single equation, maybe one or two equation but not many. So my focus is entirely on the motivation of the subject. It is not about like giving detailed description of the models theory used. I will just put a light, like what is the motivation, why we do this stuff, and then we can build our research upon, right? So let's start with this topic today. So the title of my topic is the from microscales to macroscales, understanding neutron stars via nuclear equation of state. So I'm assuming my audience is like laymen. They are not aware of all the scientific terms and physics language I'm talking about, so I will be as much simple I can. So what I want to do in this presentation, I want to create a bridge between particle physics and astrophysics. So when I say microscales, I'm talking about the physics which is happening at the level of 10 to power minus 15 meter, or roughly you can see at the level of atom. And when I talk about macro scale, I'm talking about the physics when it is happening at the level of stars, planets, and all those things. So the neutron stars are related to the macro scale, and nuclear equation of state is related to the micro scale. So we will be talking about all this in general um, in the next couple of slides. So let's start with the outline part of my talk. So first of all, I will start with the introduction part, where I will give a brief idea of what we are doing, what is the motivation. I will put some context, some historical context about this study or research. Then I will shift my attention to microscales, like the particle physics or nuclear physics regime, a different type of forces involved. Okay, nuclear force is a different separate force, but I will talk about what are the dynamics of that particular force in that regime, right? And in the macro scale part, I will talk about how whatever I'm going to talk in this presentation, what are the macro scale, what are the macro object or macro physics I'm talking about, and how they are, what are they, how many types of there are, right? And then I will try to connect these two separate regime, which looks like a separate regime, to a one regime, and at last I will just conclude it. So let's start with the introduction part. So in the introduction part, I will start with the very basic evolution of the universe, which we also call the Big Bang theory. So scientists believe that when the universe it was started from an explosion or a big bang, and we call it as when the time was started, let's say 0 second, and at that time there was an explosion from nowhere. So there is a huge debate whether it was an explosion or not. So I am not going on that. I'm not talking about that. but I will just give you a brief idea. Okay, there was an explosion or there was a singularity at the beginning, and later on, with the some event, the universe was created. And at that time, the temperature of the universe was around 10 to power 22 MeV, which can be converted into Kelvin, which is 10 to power 32 Kelvin. So just to give you an idea how Kelvin, how much temperature this is, you can relate it to the normal life temperature. So when we talk about room temperature, which is uh, let us say we have like the room temperature is 25 degrees Celsius, and if you convert it to Kelvin, then it can be converted like 3 273 plus 25, it will be around 298 Kelvin. So but if you increase the temperature like 50 degrees Celsius, so for us, for humans, it is hard to live in such an environment, right? So in that context, if we convert that into Kelvin, it will be around 325, let us say 325 Kelvin. So for us human, 325 Kelvin is a big, huge temperature, right? But here I am talking about 10 to power 32 Kelvin. So you can imagine how high this temperature is. Obviously we cannot exist there. Right. So with the evolution of time, and the universe was tiny, and with the evolution of time, it expanded, the area expanded, and since the temperature is distributed with the area, within the area, and energy is also distributed, the overall temperature of the universe goes down. And in the beginning, we have in the initial phase, we have like radiation dominated universe. But with the advent of time, with the passage of time, the radiation got converted into particles through pair production process, right? So it converted in quarks and anti-quarks, and electrons and anti-electrons, and the average temperature of the universe goes down from 10 to power 22 to 10 to power 17 MeV. And at this time, around these time scales, we got a highly dense quark gluon soup, where quarks are free, they are interacting with each other through gluons, and it is highly it acts like a perfect fluid. And with this transition, with the advent of time, with the passage of time, we get the temperature cools down, and it comes around 10 to power 12 Kelvin. Now don't worry, I will tell you about what are quarks, what are gluons. You don't have to worry about that right now, so you can assume they are kind of a particles. So they are kind of a subatomic particle which exist at microscales. And then with the further decrease in temperature, or with the passage of time, the quark gluons, as the energy is going down, they form a bound state and the bound states are called hadrons. It could be baryons or mesons. I will discuss in the next couple of slides. And the average temperature goes down around in this case, like if we talk about hadrons here, so the average temperature is around 10 to power like around 100 MeV, right? So there is the process, the conversion process from quark gluon soup or deconfined soup to hadron is called hadronization. And this is very, very important in terms of particle physics, where we are focusing, where our focus is to understand how the physics is changing in this context, how these particles are formed, what kind of symmetry they obey. So these are all the research I'm interested in. And later, after this hadronization phase, um, with the passage of time, obviously the hadrons, there are hadrons, they attract each other gravitationally, and eventually with after many years, like 10 to power 17 seconds, we we get our current universe, which is called the current state of the universe. When we see upwards in the sky, we see lots of stars there, galaxies and whatnot. So these, they all come through this process. First there is a big bang, then there's a quark gluon soup or the particle soup, then it goes to a bound state, and eventually with all those process, within the time frame, it forms the current visible universe in which we have galaxies. So the average temperature comes down to around 10 to power minus 10 MeV, which in Kelvin is roughly around 2.7 to 5. Now this whole diagram can be divided into two sections. One is called the microscale in the present presentation context, and the other is called the macroscale. So I will be focusing on these two. I will discuss the each individual part in detail, and the second part as well. So stay tuned for this. So before going further, I would like to introduce you to some fundamental concept if you are not familiar. So if you are a particle physics enthusiast or maybe a physics enthusiast, then I guess you already knew about this. But let's start with this. So we have four kind of forces in the nature, which is called gravitational force, electromagnetic, nuclear or strong force, or weak force. So the gravitational force is quite visible. We can see it in every day. So we can relate it um, very easily. So what is the gravitational force? So whenever in the universe we have like objects everywhere, and they have their particular mass. So if a object 1 has some mass and object 2 has some mass, so they are basically interacting with each other through a gravitational force, and the gravitational force is always attractive, and it goes like inverse square. It obeys inverse square law, and the formula is given in the screen. And the mediator I'm talking about here, I have shown on the screen with a star, graviton. So in every force, whenever the two objects experience force on each other, they basically exchange some particles, some virtual particles, right? And these particles are called mediators, which are the carriers of the force. And in the gravitational force case, it is called graviton. So why I have put star there, I will talk about that later at the end of this slide. What about the other force we observe in nature? So electromagnetic force, we observe the electromagnetic force in nature, like on a daily basis. We have electricity current. Currently this bulb is glowing. And also, if I can give you a simple example, so in during the party times, or like birthday, happy birthday time, we inflate the balloon and we rub it on our jacket or something, and then we can easily stick that on the wall. So why that balloon sticks on the wall? Because of the electromagnetic force. So what we have done, we have created a charge on the balloon by rubbing it, and when we put closer to the wall, due to the induction process, it creates a attractive electromagnetic force there. So in the case of electromagnetic force, the mediator is called photon. So that means if there are two charges, the photon is being exchanged in those cases, right? um, what about the third force? So before going to the third force, the first two forces are called long range forces. Like, we can feel those forces if we are placed very distance apart. For example, solar the earth can feel the gravitational force of the sun, right? And they are around 150 crore kilometers far away to each other. And similarly, electromagnetic force, we can see the light coming through, coming towards us through from the universe, from some point. And but when we talk about nuclear strong force or weak force, they are not long range force, they are short range force. So what's make them difference from the long range forces? Their effect can be observed only when they are very close to each other. So if they are very far from each other, there is no effect. So you can see from this diagram of potential energy versus internuclear distance, the strong force is very repulsive when the particles are very close, and it becomes attractive and becomes maximum in an attractive manner. And when we increase the distance further, it becomes almost zero. So strong force is a short range force, and it is only active around whenever we are talking about the scales 10 to power minus 15 meter, which is the size of nucleus. So we are in a nucleus, and then the strong force pops in, right? Then all the dynamics are governed by the strong force. Now we can see when the particles are very close, which experience strong force, they basically experience this repulsion. Why they experience this repulsion? Because of the Pauli exclusion principle. The Pauli exclusion principle says if we have a fermions, two fermions with the same spin, we cannot put that in the same orbital, so they will repel each other, right? So we have learned that in our secondary school classes, and that kind of pressure we call is the Fermi pressure or Fermi degeneracy pressure. And what are the mediator of this force? uh, it is called gluon, and it has a separate color chart that I will talk about later in this presentation. And what about the fourth force? The fourth force is called weak force. So it comes into picture whenever we want to describe the radioactive decay of heavy nuclei to a light nuclei. For example, uranium 235 into a light nuclei, then it can be described using the weak force, right? And it is also a short range force. And there is a misnomer in the context of weak force. Weak force doesn't mean it is weak amongst all the forces. Weak force is weak from nuclear force, and the nuclear force is the strongest force, and the gravitational force is the weakest force. And in the case of weak force, the mediators are, which are the exchange particle, as I told you before, are the W and Z bosons. Now, among all these forces, they are very important in the context of microscale, macroscale, and bridging them together. But I am more interested in the nuclear strong force. Why, I will tell you later. Now, uh, so we had a brief introduction about what we are trying to do and the motivation behind it, the brief introduction. But now I will talk about the micro scales. Like, what are the micro scales? I have told you about the nuclear force, which acts at the level of 10 to power minus 15 meter, which is very, very, very micro. So there is no standard definition of micro in this presentation context. I have used that word whenever I am talking about 10 to power minus 15 meter scales. Okay, so if you feel if it for you it is not easy to imagine 10 to power minus 15 meter, you can simply think like if like we are humans and we are made up of molecules, right? We have muscles, we have this skin, and the muscle fibers, let's say muscle fibers are made of molecules, and the the fibers are made of molecules, and molecules are made of atoms, and atoms are made of the nuclei are made of quarks, and are made of quarks are the elementary particle, and they are made of, let us say, energy. So energy is everywhere. But whenever I'm talking about microscale, I'm talking about 10 to power minus 15 meters. So you can relate with the particles, with the molecules, and the size of the particles. You might have seen the microscope where you can zoom in the blood, let's say, and you can see red blood cell and these white blood cell and other objects in it. So you can relate. It is thousand times deeper than what I am talking about here. So we start with the discussion of elementary particles. So this is the standard model of elementary particles. So I'm not gonna go what is standard model, but I will just tell you what is elementary particles. The elementary particles are defined as the particles who are indivisible, who cannot be divided further, right? So if you as I was telling you before, if you break atom, you get nuclei and electron. You break nuclei, you get proton and neutron, and some, let's say, hyperons. And if you break proton, you get quarks. But when you break quarks, what you get? You can't get anything, because quarks are elementary particles. Same thing is for electrons are also elementary particles, and the electron family is called leptons, and quark family is called quarks. And we have six type of quarks shown in the purple color here. Six type of quarks, and we have six anti-quarks, and each quark has three colors to it. So that makes it 36 in total. So I will be focusing on these six quarks here, and the corresponding mediator, which basically the force carrier of strong force. So so from that particle, from that elementary particle, we can construct so many particles. So we have one individual particle and second individual particle. We can form a bound state. We can form a bound state by multiple combination, right? And we cannot mix quarks and lepton to form bound state like at the before the nucleus level. So let's see. So here I'm gonna talk about the particle zoo. Like as I told you, we have so many particles, fundamental particles, and by combining them in a multiple way, we can create like a lot of particles. So let's see. So on the fundamental level, we have leptons and quarks as an elementary particles. Quarks exist in three colors: red, blue, and green. And these colors are just to understand a different property. They mimic a different property at the mathematical level or abstract level. They do not really represent color. So leptons can be divided further in three leptons: electron, muon, and tau. And neutrinos, and their neutrinos can be divided in terms of electron neutrino, muon neutrino, tau neutrino. So for each particle we have antiparticles. I have not shown that antiparticles here, they are understood. And for quarks we have six quarks, but here I have only shown three quarks. Why three quarks? Because I am interested in SU3 symmetry right now, because when you talk about SU6, let's not talk about SU6 but just 6. So 6 up, down, strange, top, bottom, and charm. So the last three quarks are very heavy, so they readily decay into their lighter version, which is up, down, or strange. That's why we do not discuss them. So the bound state what we get in nature in abundance are from up, down, and strange quark. So we have three quarks. So from these three quarks we can make like a lot of combination through permutation and things. So they have to respect some symmetry. So I'm not gonna bore you with the details of symmetry. So I'm gonna make it simple. So up, down, strange quark can collectively make bound state, and they are called hadrons, which can be divided further into two categories. One is called meson, another is called baryons. What is the difference between mesons and baryons? Mesons are the bound state of two quarks, one quark and one antiquark. And baryons are the bound state of three quarks. It could be three quarks, it could be three antiquarks, but there is no mixing between quark and antiquarks. So mesons and baryons are colorless. So three quarks make it colorless. Like when you mix red, blue, and green, the colors, it gives you white. And when you mix quark and antiquark, it basically cancels out the net color, so that they are colorless. And meson can be further divided into pions, kaons, and eta. And baryons can be divided into nucleon, hyperons, and resonances. So what are nucleons? Nucleons can be divided into protons and neutrons. Hyperons are also nucleons but with the baryons, but with the strange quark in it. So we have sigma, cascade, and lambda in the baryon section, and we have resonances as well, which are the higher excited state of the nucleons or hyperons, or collectively you can say baryons. In the left side, in the meson case, I have not shown like all the mesons. There are several categories of mesons like pseudoscalar, scalar, vector, actual vector. Here I have only shown pseudoscalar mesons like pion, kaons, and eta. Why have not shown other? Because they are heavy. And the pions, kaons, and eta are the only meson which are abundant in nature. We have vector mesons as well, but axial vector mesons are not very abundant in nature and they are heavy. So here it represents the particle zoo. So let me tell you honestly, I have only shown some particles here. So it is a particle zoo, it is a mess of particles, like higher resonance state, higher mesonic states. So you can see, like, we have a up quark, we have a strange quark. How many combination can you make, like up, down, and strange? We can make up, anti up, up, anti down, up, anti strange, or so many. So it is like you have so many combination and you can create particles out of it, but they have to follow some necessary laws, necessary symmetries, right? So this was about the particle zoo here. Now the fundamental question arises, like, how do we know, like, there are so many particles, like, here I have given you like 20-25 particles. How do we know? So at the micro level, how do we know, like, tau neutrino is different from muon neutrino, or pions are different from kaons, or sigma is different from proton? How do we know? For this we have to do experiments. We have to design a theory which gives us this differentiation, distinguishness, or we have to also perform an experiment, right? So to understand that, like, if we want to understand what is inside blood, so we go to a pathology shop and we ask, okay, look into my blood and give me the details about what kind of concentration of hemoglobin it has, or what kind of concentration of red blood cell and all these things. So we do an experiment to our blood. Similarly, in microscope, obviously. Similarly, in the particle physics, we want to know about, like, what is inside our nuclei. We need something, some experiment to tear it down and see what is inside, right? So which what we call it is as a particle microscope. um, so it is a, like, layman term. It is not called particle microscope, it is just put here to give some context, right? So basically these are called hadron colliders. So we have, like, so many hadron collider in the world, but I'm gonna show two main hadron colliders which are of great characteristic, great potential, and have given many new advents in the field of particle physics. So on the left there is a large hadron collider, on the right it is a relativistic heavy ion collider. So large hadron collider is located in CERN, Geneva, and I was lucky, I got a chance to visit there. I went to CMS and I saw the detector myself. I was very lucky enough. And on the right side, this is relativistic heavy ion collider in Brookhaven National Laboratory in USA. So what makes them special? So what are these hadron colliders? So I told you hadrons are basically combination bound state of quarks. So we have hadrons, we want to know what is inside that hadron. How can we do that? We cannot just simply put it under the microscope and see what is inside it. We have to smash it together at very very high energy, and when it collides with itself or some particle, then it goes through a defragmentation, and through the defragmentation we can see what kind of particle it has emitted, what kind of energy it has emitted. From the analysis of that we can understand, okay, these were the particle that was emitted, and we can construct something meaningful out of it. So the characteristic of large hadron collider, it is a very big project. It has a 27 kilometers of circumference of tunnel with the beam line where the particle is accelerated, and it is 100-meter beneath the surface of the earth. On the other hand, relativistic heavy ion collider is not that big, but it is still meaningful for colliding light nuclei. And in that case, the relativistic heavy ion collider, the circumference is 2.4 miles, and in both the cases, the beam, which consists of, like, many projectiles, many particles, like, let us say hadrons, are accelerated up to uh, near to the speed of light, like let's say 99.9%. Why are they accelerated up to 99.9% speed of light? Because we want to get as much energy, so that when we collide them we can get the maximum result. We have the energy and it can penetrate through the hadrons, and we can get the internal composition of the particles. So it is very hard to collide one particle to other particle at microscale level, like around 10 to power minus 15. So what we do, we collide billions of particles from the left, from the right. So we not we I mean not me. So the scientists basically put a hadron, like a projectile, into some beam, and they accelerate it over again and again. And similarly, the other particle is also accelerated in the opposite direction, and when they have like the extremum velocity, um, energy, then they are aligned to each other with the magnetic field and they are smashed together. Okay, and from that we have a different experiment located at different point, like CMS, LSCB, Atlas, Alice, and all those things. And similarly, Phobos, Jet Target, RF Star, and Phoenix, and we collide the particle at the particular experiment. So it depends upon what we are interested in. So all each and every um, experiment is dedicated to a separate project. So from analyzing the data, that scattered data, the defragmentation fragmented data, the experimental physicists, like they do the analysis and they sort out the meaningful information from all those the information. They subtract the background and they got to know, okay, what is actually happening there, what kind of particle was emitted, what kind of different property it has, and we get the final analysis. So, continuing the discussion about heavy ion collision, which is also called reverse Big Bang. Why it is called reverse Big Bang? Because we are creating the recreating the condition which existed in the during the beginning of the universe, right? So I will tell you how. So in heavy ion collision, we collide heavy ions. Heavy ions are the gold, could be like gold nuclei or lead nuclei. So it is accelerated up to the 99% of speed of light, and due to the relativistically high speed, they are Lorentz contracted. I'm not gonna talk about that, but I will just skip to my presentation, my animation here. So this is a very beautiful animation about how heavy ion collision works. So basically, we have two different heavy ions. They are together, which are made of different particle, and they are collided at very high relativistic speed. And at such a relativistic speed, they have huge energy. At that huge energy, they create a fireball with a high temperature. They act like a fluid, and eventually there is a defragmentation, and that defragmented particles or energy reaches to detector, where we observed and analyze the data. So in the next slide, I have put different parts of this whole process to understand it better. So we start from the beginning. So before collision, we have two heavy ions which are made of some particles like nuclei, tiny nuclei together. So we collide them together, and we collide them at relativistic speed. They have like high temperature, and when we collide them, we get something like this, which is on high temperature, and it due to the high temperature, the heavy ion is not more there. So heavy ion is gets converted into quarks. So it get converted into its more elementary form. So with the advent of time, the area is expanding, and this whole system, the fireball of gluon or quark and gluon, behaves like a perfect fluid. So it flows like its flow is like a collective flow. And further, with the passage of time, as the energy goes down, area expands. The quark gluon plasma get converts into the quarks basically get converts into hadrons, which are the bound state of quarks, right, through the process called hadronization. Now you can relate this diagram with the previous diagram about the evolution of the universe, where we have the same characteristic, but it didn't start with the explosion. Like in this time, the heavy ion collision time, it didn't start with the explosion, but with the collision of two heavy ions. But in the case of evolution of the universe, the Big Bang slide, it started with the bang. Okay, so that's why it is called creating a reverse Big Bang. So what we do is we have a hadronization phase here. Now again, hadrons are forming, different hadrons are forming with the time. This is the time scale in Fermi by C. And after some time, after the hadronization, the particles are basically interacting with each other. So let's say proton is converting into some other particle back and forth. So there is a chemistry that is changing, and similarly, the particles are colliding with each other kinetically. They are transferring the energy. But after some time, around 10 Fermi by C, there is a chemical freeze out. That means the particles are not converting. The chemistry of the particle is not changing overall. So if a proton is changing into neutron, let us say, there are equal reaction that proton is changing into neutron, and there are equal reaction that neutron is changing into proton. So overall, there is no change of chemistry. And similarly, further, with the passage of time, there is a kinetic freeze out. The kinetic freeze out is the freeze out when the particles, the whole bunch is very far from the whole bunch. The size of the whole bunch is increased, and they are very far from each other, so that there is no collision between the two particles, right? So that's the process when we call the collision has achieved kinetic freeze out. Now, as a nuclear physicist, so this is experimental high energy simulation, right? As a nuclear physicist, you can see, we are talking about a fluid here. So we said we use some term like perfect fluid, collective flow, fireball, all those things. So whenever we are talking fluid and gaseous or plasma, so we are interested in the thermodynamics of that. So we are interested in the temperature, what kind of temperature that fluid has, what kind of volume that fluid is in, what kind of pressure the fluid is experiencing, and what is the energy per unit volume for that fluid, right? So we are interested in that, and this information tells us about the equation of state of that particular system, particular physical system. And from that equation of state, we can make something meaningful, which is called phase diagram. So phase diagram helps us to understand the dynamics of that system. For example, we can take a simple example of water phase diagram. So in the left side, you can see what pressure versus temperature, which is the phase diagram of water. So it has basically three phases: solid phase, liquid phase, and gaseous phase. So in our common life, it is very commonly observed that, like, we have ice, we can create it in the fridge, and when we put it outside in a normal room temperature, it gets converted into liquid phase. So there is a phase transition. And also, if you boil the water, it gets converted into gaseous phase if you increase the temperature. So temperature is very common understanding for us, because we can see it directly, but pressure is a little bit more conserved. So let's try to understand in this phase diagram. We know the thermodynamics of water, we know the pressure and temperature, and when we plot it, we see if the pressure is low and the temperature is low, the water, the ice, the solid phase of water doesn't go to liquid and to gas, but it goes to gaseous phase directly, right? But if we have a high pressure and low temperature, moderate temperature, then it undergoes a solid to liquid phase transition. And if we increase the pressure temperature further, then it goes from liquid to gaseous phase transition. And these are the point. This red point is called the phase transition line or coexisting line, where solid phase and gaseous phase can exist together. Similarly, here in this blue line, liquid phase and gaseous phase can exist together. And at this point is called triple point, where all three phases can coexist together. and this point is called critical point, which is also called, these are the phase transition line, and this is called the the critical point, right? Higher order phase transition. And after that we have no clear phase transition boundary, and in this case we call it as a coexisting crossover phase, where liquid and gaseous phase can exist together. Now, on the right hand side, I have plotted the same diagram but for the strongly interacting matter, which is called quantum chromodynamics, the matter that obeys the quantum chromodynamics. So, quantum chromodynamics is a theory to describe strong interaction physics. So, on the right hand side, we are more interested in temperature and baryon chemical potential, not pressure. We can also make this plot in pressure, but here I have presented in baryon chemical potential. So, baryon chemical potential is a little bit difficult to understand for, you know, non-physicist, or for early career, not early career, but early physicist. So I we can think it in terms of density, right? So temperature versus density, here the density is increasing towards this side, and we can see the temperature is in MeV and baryon chemical potential is in shown in GeV, or the density is in shown in Fermi inverse cube. So we are I guess we are not much familiar about electron volt unit. So here I have presented like 1 electron volt is equal to 10 to power 4 Kelvin. So instead of writing 10 to power 4 Kelvin, 10 to power 10 Kelvin, it is easier to write just MeV. So it is a very convenient unit when we talk about nuclear physics. So in this diagram, we can see there is a phase transition line, this red line, which basically differentiates, which makes a boundary, clear-cut boundary between a hadronic phase and a quark-gluon phase. So this phase where we have quark-gluon phase, like these dots, is representing deconfined quarks, whereas these bound state particles like UUD represent the confined phase or hadronic phase. So and from here to here we have a phase transition line, clear cut, and then we have a critical point here which is assumed, which is anticipated from this water diagram, and after that we have a coexisting phase between hadrons and quark gluons. Now on the basis of temperature and baryonic density, the phase diagram can be categorized in um, different regions. So this is the region where we can study the quantum chromodynamics through heavy ion collision when we have high temperature and no baryonic density. And these are the region not shown here where we can study from the fixed target experiments, where we can generate high baryonic density and moderate temperature. And these are the region where we can study the quantum chromodynamics phase diagram through the neutron star mergers at high temperature. And these are the region where we can study the quantum chromodynamics equation of state or phase diagram through the neutron star physics, which is around t is equal to 0 MeV. So this is very important for this region is very important for us for this particular presentation. And here I have represented the same diagram, but the context is a bit different. So the diagram is between temperature and baryonic density, and I have divided the baryonic density by some nuclear saturation density to make it unitless and easier to understand. So this diagram represent the theories or experiment that can use to describe strong interacting physics in a different regime. So this is the same plot as this: heavy ion collision, neutron stars, neutron star mergers. You can see heavy ion collisions, neutron star mergers, this blue one, turquoise one, and then we have a neutron star here. Now the quantum chromodynamics is different from all other theories. So in all other theories, for example, gravitational theory, it doesn't depend upon the distance. So that's why it is same irrespective of distance. I mean, the coupling constant doesn't depend upon the distance. But in case of QCD, the QCD is strongly correlated to distance. The coupling constant is strongly correlated to distance. In this case, the coupling constant of quantum chromodynamics is very very small, so that the particle interacts very weakly. But here the coupling constant is very strong, so the particle interacts strongly. So that makes this quantum chromodynamics different from all other forces, strong force from all other forces. And due to this, we cannot apply a same single version of QCD everywhere throughout the strong interacting phase diagram. So we have different theories which are applicable to different regime. For example, we have lattice QCD, which is applicable around this region. We have heavy ion collision experiment, which can describe physics in this regime, this Brown regime. Then we have a perturbative QCD, which can describe physics in this regime, high density, high temperature. And then we have low energy nuclear physics experiment, which can describe physics in the nuclear saturation level. Then we have chiral effective field theory at very low temperature and density. Then we have neutron star physics, which can describe the strong interacting phase diagram around T is equal to 0 MeV and up to uh, 8 times nuclear saturation density, which is very very dense. And then we are left with this white region. This white region is the region where we cannot apply a direct fundamental QCD technique or first principle. So in this these due to some limitations, so I'm not going to talk about that here. So for this we need to rely on some effective models, which are the models based on QCD fundamental symmetries like chiral symmetry breaking and explicit symmetry breaking, as well as trace anomaly. And by modeling that, modeling the model parameters and fitting it to the certain constraint coming from this experiment, we can try to explain what goes inside this region. And we can also say, like, okay, the lattice QCD doesn't say anything about the criticality here or the phase transition here, so we can also try to understand the criticality or the phase transition from this point, these effective models. So this was all about the micro physics side of like strong interaction physics on nuclear force. Now I will shift to the macro scale or macrophysics part of this talk. So so we understood so far the nuclear force, what is nuclear force, how it is related to the what is the thermodynamics of it, and the equation of state, the phase diagram, all that. Now I want to learn, when I say macro scale, what I'm thinking about it. So whenever I'm saying macro scale, I'm thinking about the particles who exist at very macro level, like stars, okay, planets, stars, interstellar dust, accretion disk, black hole, and whatnot. So to understand this, we need to understand the macro scale side of this presentation. We need to understand how stars are formed. So if you remember in the beginning, I was explaining the evolution of the universe diagram, and then I showed this phase hadronization to galaxies phase, right? And how this conversion basically happened is given by this slide. So after the hadronization process, the universe was abundant of proton, or we can say hydrogen nuclei, and this interstellar dust is also called nebula. And because of we have like huge thousands of kilometer dust uh, through the universe, and they are gravitationally active because the hydrogen has a mass. So they start to coagulate with each other, they attract each other due to gravitation. And we have two cases for that. If we have a very high mass nebula, then we goes downwards. If we have a low and medium mass nebula, if we want to produce a low and medium mass star, then we have a first, the top phase. So the particles in the interstellar dust, they attract each other. They make a they try to be stabilized. They make a circular shape, the spherical shape. And when the particles are attracting each other, they start to become very close. And when they are very close, the nuclear force comes into picture. The nuclear force engine pops up. So when they are very close, they are repelling each other, and when they are tiny bit apart, then they are also experiencing this attractive force. And at such condition, at such high temperature, um, the nuclear fusion began to start. So in that case, the hydrogen starts converting into helium, and that is I'm here talking about the main sequence part where the sun is located. um, in the HR diagram you can see. So yeah, sorry, I was disrupted by my phone. So here the nuclear fusion starts up, right? And when nuclear fission starts up in the core, the metals start converting from hydrogen to helium and so on. So we have two forces attracting in this case. One is the nuclear force that is keeping the nuclear fission going, and also fusion going, and also it is repelling each other, right? And the gravitational force is attractive. So gravitational force is trying to make the body compact, and nuclear force is trying to make it apart. So these the interplay between these two forces keeps on, and as long as the forces are balanced, the star is stable. uh, and in the next phase, when the nuclear fission cycles are continuing through, and we have hydrogen to helium cycle, helium to carbon cycle, and so on. If we talk about the low and medium mass star, let us say sun, so we have hydrogen to helium cycle, then we have helium to carbon cycle, and at some point of time the nuclear fuel will burn up in the core. So there is no longer the nuclear fuel, and we have only left with the gravitation force, because we don't have a strong force that is repelling at the core, and we have only the gravitational force which is pushing the particles together, right? But in this case, after the fusion, we have like ginormous gas of particle that is surrounding the core, and they are very far from each other, so the gravitational force is not that much active around that. So eventually with time, when we have no fuel left, we have less fuel left in the core, the outer gases of the star like spreads out, because they are weakly interacting due to gravity, they are not experiencing towards the core. So they spread out towards the vicinity, they mix up with the universe, and we get something like this, which is called planetary nebula. And in that core, after some time, after some years, the core is intact, and it is without any gaseous structure around it, and this type of star is called white dwarf. Why it is called white dwarf? Because in comparison to other stars, it has very less size or radius. Okay, so what about the next process? So we have the similar process. We start with the high mass star. We have a main sequence. It goes to a main sequence, and since this time we have a we have huge um, mass nebula to start with, interstellar to start with, the gravitational force is enormous, as well as the nuclear force is enormous, because there are more particles at the core. And it goes through the same process, but this time, due to the heavy gravitational force and more nuclear fuel, it basically uh, gives the red supergiant, but not the red giant phase. So in the red giant phase, it is a gaseous cloud with this intact core, with the strongly interacting core, but around that, this is a remnant of the nuclear fusion process. Now the star is stable until the nuclear force and the gravitational force are balanced. The moment they are not balanced, the star will explode. It can explode internally like core collapse or towards outwards. It depends upon what kind of force is winning it, right? There is an interplay between gravitational and nuclear force. Now the star is there's a gravity force that is keeping the star together, and there is a repulsive force which is keeping it away, right? Now um, so when there is no more nuclear fuel left in the star, in the core, and it cannot, I will say not like zero nuclear fuel, there is not enough nuclear fuel so that it can sustain, it can provide enough repulsion. What will happen? Gravity will win over, and there will be a core collapse. In that core collapse, this explosion will occur, and this is called core collapse supernova. This is a huge explosion which can be seen through a naked eye if you are lucky enough in your lifetime. And when this happens, the core collapse supernova, the gravity basically crushes the matter together, and the shock wave basically hits the core of the repulsive core of the star, and it bounces back, right? So that's why it is a huge explosion. Now um, with the result of that, as a consequence, we get neutrons, we get two bodies. We can get, like, if the core is, the mass of the core is high enough, we get neutron star. Or if the core of the star is very high, then we get black hole. Now we have learned about the formation of stars, like how different stars are born: white dwarf, neutron star, and black hole. But in uh, the case of this presentation, I am interested in neutron star. I will tell you why. Because neutron stars are the particles. Neutron stars are the gravitational body that are closely related to the strong interacting physics. So they can tell you a lot about strong interacting physics, or QCD. White dwarf can also tell us about it, but the neutrons are the main candidate. Black hole are, on the other hand, more towards the cosmology sides of it, or the dark matter side of it. So as I told you, I'm more interested in the neutron star. So let's talk about it, and let's talk about why it is special. So here is a comparison of different gravitational body, and obviously they are not to scale. I just fit it into my slide. so before talking about it, I would like to tell you about some units. Like, first is the nuclear saturation density. So nuclear saturation density is a unit that we use in a particle or nuclear physics when we describe nuclear matter. Um, so one nuclear saturation density is 1 Fermi inverse cube, which is equivalent to 10 to power 17 kilogram per meter cube. So you can think you have 10 to power 17 kilogram of a matter that you can fill in 1 meter cube of volume. That much dense matter I'm talking about here. So when I say one nuclear saturation density, so this is one thing. And the other thing is the mass unit, which is one solar mass. One solar mass is equivalent to 10 to power 30 kilogram. So you can also imagine how huge this mass is. So why I'm telling you about all these units? Because whenever we talk in such environments like macro or micro, in macro case, when we talk about sun, we don't say 10 to power 13 kilogram it is holding. We say the mass of the sun is one solar mass, which is very convenient to say. Similarly, in the nuclear level, when we talk about the density of a star, we don't talk about it has like 10 to power 17 kilogram per meter cube of matter in it. We say it has 8 times nuclear saturation density, or 1 time nuclear saturation density. So which is very convenient for that particular regime, for that particular scale. Now coming back to our comparison slide, so we have a sun. We know radius of a sun is 10 to power 6 kilometer, and the mass of the sun is around 1 solar mass. And similarly, the radius of earth, if we compare, is around 6400 kilometers. We can say 10 to power 3, 10 to power 4 kilometers, and the mass is 10 to power minus 6 solar mass. So the radius of earth is very very tiny as compared to sun, and we can fit 1.3 million earths in the sun. So you can imagine how big sun is. Now when we talk about neutron star, they are very interesting in terms of what? In terms of the radius of neutron star is just 10 kilometers. The radius of earth is 6400 kilometers, but the radius of neutron star is roughly around 10 kilometers, and the mass is extremely high. It is two times the solar mass. So you can say we can fit two suns in just 10 kilometers. If we can squeeze two sun in just 10 kilometers, that kind of gravitational body we are making are called neutron stars in terms of density. So to scale, we can fit 260 million neutron star in one Earth, and you can imagine how many neutron star will take to fit in one sun. So this is how dense the neutron star is. So there is a saying that if you take one spoon of neutron star, it would weigh thousands of kilograms, thousands or like millions of kilograms. So that is um, how huge neutron stars are. So what are neutron stars? I will talk about that later, but let's say how it was discovered. What are the observations pertaining to it? So on the right hand side, I have shown some observations from different neutron stars. So I'm not gonna talk about like what is X-ray, binary, optical binaries, double neutron star, all that thing. But you can see we have different names of the neutron stars here. It has certain meaningful nomenclature, and most of the neutron star have mass around 1.4 solar mass, and there are huge uncertainty bands, and these have been um, calculated with you by using the Kepler's law. So how the neutron star was discovered? So there was a graduate assistant, like PhD scholar, working in Cambridge. So she discovered it for the first time. She discovered neutron star, which is also called pulsar, in 1967. So she was like working on her research on a daily basis, and she detected regular radio pulses from a radio telescope which she helped construct. So she thought it is an interference. So what she was observing is, there is in the detector she was observing there is a regular peak that is coming through at a regular interval. So she thought like it could be an interference, or it could be a man-made interference, or terrestrial radio interference, because that could not be, if it is a coming from the universe, from some star or something, it should not be that much regular, right? So um, she opted that out because she thought like it could be a man-made interference. But the signals were very extremely regular, so it could also resemble artificial sources. Some at that point, some of like humorously thought like the source should be named as little green men, because it can be of extraterrestrial origin, maybe of some aliens are giving some signals to earth. But later it was realized it is a pulsar. And let's talk about like what kind of neutron stars we have two neutron stars. One is called pulsars, another is called magnetars. We have several kinds of neutron star, but I have only shown two neutron stars here, pulsars and magnetars. There are short gamma ray burst neutron stars. I have not shown it here, but the main types of neutron stars are here. So neutron stars are charge neutral. That means the overall charge of neutron star is zero. And pulsars pulsars are the neutron stars which basically, yeah, which so let's see through it in this way. So pulsars has a magnetic field around 10 to power 12 Gauss, right? And they rotate very fast at regular interval where frequency is 700 hertz, and it means like it rotates 700 times a second. And due to the magnetic field, it 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 has a gamma rays burst, venting out through the magnetic axis, and it is also tilted to its axis. uh, that's why the x-ray burst is tilted. So it expels radio pulses due to rapid rotation. So you can see the rotation of the, sorry, we can see the rotation here. So why it is called pulsars? Because when we are observing that from the earth, so when the pulse is facing towards us, because it is tilted, if it is facing towards us, it gives us a pulse, and when it is not facing towards us, it is not giving us a pulse. So that's why it is called pulsars, because it is pulsating. And the second category we have magnetars. So magnetars are also pulsars, but they have very huge magnetic field, 10 to power 14 Gauss. So we can compare that magnetic field to Earth, which is around 1 Gauss, which is very low. So this is very high magnetic field which exists in the universe naturally, and the rotation velocity of magnetars is comparatively slow as per pulsars, around 1 hertz, and they also show X-ray burst due to very high magnetic fields. Now, I have shown you about the masses of the neutron stars and the category different types of neutron stars. Now let's talk about how do we know the masses and radius of a neutron star. There are different mechanism to do that, but I'm gonna talk about the latest one. So what we understood so far, we have a pulsar. Whenever the pulse is facing us, like towards the earth, we record a pulse, and then we say, okay, this is a pulsar. We measure the frequency of rotation, all that thing. But if the object is very far enough, like in 10,000 thousands of light years away, how do we know about what is the mass and radius of that particular neutron star? How do we know about what is the composition of that gravitational body? So it is very challenging to understand macrophysics observables like mass and radius. So the composition is very far away. So we have an experiment located on International Space Station. We can see this experiment, which is called NICER. The NICER stands for the Neutron Star Interior Composition Explorer. Basically, it is designed to understand what is inside the neutron stars. So why we are interested very much about the composition of neutron star? We are interested what kind of matter is making this thing possible, that highly dense system is stabilized, right? How can the matter can be so dense? What kind of matter it can retain that is so dense? So we can we can calculate the mass and radius of a neutron star through NICER using the pulse modeling of hotspots. So luckily on neutron star we have X-ray burst, that is one thing. On the other hand, we have some hotspots of like emerging plasma, like solar flare. When the star matter interact with magnetic field, we get some hotspots. Now, by observing the hotspot through the experiment, the detector, we can see whenever the hotspot is facing us, it gives us a pulse, and when it is not facing us, it doesn't give us a pulse. Very simple, right? But thanks to the general relativity tells us whenever there is the mass of an object interacts with space time, and whenever we have huge gravitational body, basically it disrupts the space time, and it can show us the phenomena like the gravitational lensing, the bending of light, and this is a very beautiful example here. If we have a weak gravity, if we have a light star, we can see whenever the hotspot is facing us, we will get a bright spot, but when it is not facing us, we will not get any pulse, we will not get any spot on our detector. But if the star is very dense, it has a strong gravity, even if the hotspot is not facing us, we still get some light. Why? Because of the gravitational lensing effect. So we have a different concept from general theory of relativity, which helps us understanding the things which are beyond our thinking, like how can you measure mass and radius by just observing the pulse. So we have different processes. We can observe Doppler shift, gravitational redshift, which is the Doppler effect in case of gravitation. And we can also observe gravitational lensing as I described earlier. And we can also observe Shapiro delay, which is the time delay of a pulse when it is coming from the star to the earth when it interacts with the gravity. Now, gravitational lensing or GTR gives us gravitational lensing, and it can mathematically relate to a parameter which is called compactness, which is the ratio of mass by radius. So, the gravitational lensing, which we can measure experimentally by combining it with theory, it can give us information about the compactness of a star, like how compact the star is. And by knowing that, we can calculate the mass and radius of a neutron star. So the process I'm saying it looks like very simple, but in reality it is a very complex process. Different collaboration from around the world works on that. They take like couple of years to understand the data and finally make a plot like this beautiful plot, which is the plot between mass and radius. And for one neutron star 6620, the two groups have shown the results with the uncertainty band, and the other neutron star 451, 1.4 solar mass and 2 solar mass, the two different groups have shown the results. Okay. Now, so far we got to know about the microscale part of this talk and macroscale part of this talk, right? Now we would like to bridge these two. So in the microscale part, we understood we have strong interaction physics, which is responsible for all the microphysics dynamics. But in the case of macroscale, we understood like we have a neutron star, we have compact star, where there is a role of strong interacting physics, and we are more interested in the radius and mass. Now, is there a way we can connect those two different items, different things together? Like, can we connect neutron star to microphysics or vice versa? Can we know what is inside the neutron star? What is the composition of a neutron star? So this is what we have to talk now. So before going to that, let us understand um, the how the four fundamental forces exist or interact in neutron stars. So first of all, let's start with the gravitational force. So we know, so neutron star is a heavy body, right? It has a huge mass. So it interacts with density with the space time, and we can see when we talk about two neutron star system, binary neutron star, they are basically orbiting each other around the center of mass, and they start to lose energy. When they start to lose energy, they emit gravitational waves. So this gravitational waves travels through the universe and eventually reach the earth or anywhere. So this is how gravitational force is in the picture. And then we have electromagnetic force, which is through the electromagnetic pulses. So we know from the magnetic axis, there is an X-ray burst in the neutron stars, which is due to the magnetic field, which is electromagnetic force. And then we have a strong force role in the neutron star, which is very, very important. So we anticipate like what kind of matter should be inside the neutron star when it is so dense. So can it obviously it can, if the matter is very compressed, like highly dense, it cannot be an ordinary matter. It should be a strongly interacting matter, because we are talking here about the distance 10 to power minus 15 meters, in terms of density. And there could be a nucleons, there could be a strange quarks or quarks. uh, that's how we have a strongly interacting matter or strong force inside the neutron stars. And we can also think why neutron star is stable. So if the gravity is huge, there should be enough repulsion from somewhere so that it can sustain. So the repulsion is coming through the nuclear force, the strong force. Then at last we have the weak force, mm, which is governing the neutrino emission. So while I was describing the formation of star, I skipped from supernova part to the neutron star part very quickly, but it is a very long process. So after the supernova, the core of the star is still hot. It is called proto-neutron stars, and in the proto-neutron star uh, phase, the star has protons and it is hot. But with the passage of time, the star loses its energy, and I'm talking about here years, like thousands or millions of years. This process take times. So we have protons. So protons goes through inverse beta decay. They capture the electron and they get converted into neutron by the emission of neutrino. So the neutrino carries the energy, and eventually the temperature of the neutron star gets cooled down. So this process takes a long time, and with this process, the proton neutron star becomes the neutron star, and the force behind this is called the weak force. So this is how all the four forces acts inside the neutron star. And now I would like to give a rough picture about what a neutron star, what is the composition of a neutron star, right? This is a conjecture diagram, this is not a reality. We anticipate, like, in analogy to the earth, I have shown here the different parts of the neutron star that we can anticipate. So we have atmosphere, we have outer crust, inner crust, outer core, and inner core. So we can see, as we go from the surface to the center of the star, the density basically increases, obviously. And in the atmosphere, we have, it is anticipated that it has mostly atoms. And when we go inside, so when we go inside, we are crushing the matter. So in the outer crust, we have heavier nuclei or free electron, and when we crush it further, we can get free neutrons, because the neutron got dripped out from the nuclei, and it can exist freely in that case, in that inner crust. And we have electron as well as some atomic nuclei. But in the outer core, when the density is high enough, so that there are no atomic nuclei, but just the neutrons and neutrons in abundance, and they form like a plasma there, they form like a neutron rich nuclear matter or nuclear fluid. And this is the biggest portion in the neutron star, which consists of neutron rich nuclear matter. That's why the star is called neutron star, because it contains neutrons in abundance. And then we have an inner core. The inner core density is anticipated to be around 5 kilo sorry the density is anticipated to be around 10 times the nuclear saturation density, which is very very huge, like 10 to power 18 kilogram per meter cube. And due to that high density, it is anticipated that the star can hold, in the inner core, the star can hold uh, not only nucleons, but it could be hyperons, because the inverse strange decay can be possible in such conditions. We can also have Mason condensates, the resonance baryons, delta particles, as well as it could be a possibility that we have deconfined quarks. Now we know the composition of the particle. If we know the composition of particle, that means we can describe the pressure, the temperature, energy density, entropy density. That means we have an equation of state. So can we get information about mass and radius? Can we relate these two different quantities like micro and macro? Yes, we can. How? We need to know some conditions, right? We need to know some boundary conditions. So we know that the pressure at the surface of neutron star is zero, obviously, any gravitational body, and pressure at core is maximum. So these are the two boundary conditions that we will use to calculate microphysics from microphysics. Now, luckily, we have this equation which basically bridges the microphysics and macrophysics part, macroscale part of this whole picture. So this is called Tolman-Oppenheimer-Volkoff equation. So the TOV equation describes the structure of a spherical non-rotating body in hydrostatic equilibrium. So what TOV equation does, it defines the structure of a spherical body. So we are assuming our star is a spherical body, has a spherical body, and it is non-rotating, but in reality the star is always rotating. So we can ignore the rotation for some extent under some valid assumption, and it is in hydrostatic equilibrium. So we have these two equation which are called Tolman-Oppenheimer-Volkoff equation or TOV equation, and we can see there is a energy density and pressure which is the microscopic variables, and we have the mass and radius of a neutron star which is a macroscopic observable. So we have the micro properties in here and the macro property in here. So from the theory we can calculate pressure and energy density of the matter, and we can put that variables in that equation, and from that we can simply calculate the macro properties of the neutron star. So by just using the theory we can calculate which should be measured experimentally in our mind, right? But this is the power of theory. So here I have represented the input and output of this TOV equation. In the left side you can see the plot is called equation of state between pressure and density, and the equation of state is developed by some model, let us say model or theory, which has given these curves. And so in the quantum chromodynamics phase slide I told you about the QCD is not well established so that it can describe all the phases of the matter, all the regions within the QCD phase diagram. So we have chiral effective field theory which is valid, which gives us very good result in low density regime, low temperature regime, and perturbative QCD which gives us result about high temperature and high density regime. But here the system we are talking about is at t is equal to 0 MeV effectively. So we have like chiral effective field theory at low density and perturbative QCD at high density, which gives us the constraint to the equation of state. But there is no theory in between this region, so that's why we have to rely on the model. And one other method is that we can use a parameterized equation of state which doesn't belong to any physics, but we simply which doesn't have any microscopic information like what kind of matter it is, but we simply join the two curves, and as long as the causality is retained. And obviously we can see from this chiral effective field theory the equation should be stiffer in this region, and after the middle point it should be softer so that it connects well. So we can create a band here that allows the causality from a parameterized equation generator, and we can put all those information. We have also other equation of state from different models, like for different degrees of freedom. Whenever we are only considering nucleons, red one, when we are considering only quarks, when we are considering hyperons as well, when we are considering quarks and nucleons, we have these different equation of state. So we can see in this case hybrid, we have this phase transition here as well. So when we put this equation of state into some TOV equation, in TOV equation, as an output we get mass radius. So we can see in the right hand side mass and radius plot, and we can see this huge band which is corresponding to this equation of state. So as I described, it doesn't contain any physics composition about, it doesn't contain any physics information about the matter, but it is just to understand what is the an not error band, what is the left, what is the maximum mass, what values can it have, like when it goes to the maximum right or maximum left. So it gives you a band. So all the valid equations of states should goes inside the band, right? And when on the right hand side we have the same labels here, we have different equation of states. So we can see if we change the degrees of freedom here, it changes the value of the maximum masses. So we can say nucleon has the maximum mass, then we have a quark star, then we have a hyperonic makes it softer, and hybrid makes it more or less softer, right? So how we do TOV equation, how do we solve TOV equation? We basically choose a central energy density from this equation of state plot. Let's say we start with this energy density, which is the pressure of core at maximum, and this is the pressure of core at minimum. And we put that table in the TOV equation, and it gives you a point in this curve for a particular star. And by choosing the different central energy density from going from left to right, we put a lots of dot here, like which each dot represent a different star, and then we connect these dots, then we get the maximum star it can have from this equation of state. Now in this plot, here I have shown my original research from this paper, where we have calculated the equation of state from a relativistic mean field model, which is called chiral mean field model, which I am working with my professor, supervisor, Professor Veronica Rexheimer from Kent State University, Ohio. And also I work in the same model with Dr. Arvind Kumar in NIT Jalandhar during my PhD. So this represents the equation of state in terms of pressure and energy density, and here I have only nucleons. When I have put star, that means there are no hyperons, but in RC4 and RC4, this dash and yellow curve, we have in one we have hyperons, in other we don't have hyperons. So we have different equation of states here. Now using that equation of state in the mass and radius diagram, we can calculate the mass and radius. And here I have put the regions from different experiments, the constraints, and we are ensuring that our mass and radius curve goes through the constraints. We are only interested in the equation of state that can reproduce the constraints, right? So we see whenever we are talking about the equation of state without the hyperons, we get a higher maximum mass. But when we add hyperons, I have not shown actually the hyperons here, so you have to trust me. When we add hyperons, it gets softer. So when it gets softer, that means this is softer, this is stiffer. When it gets softer, it gives less maximum mass. The equation of state, so the conclusion is the equation of state should be stiff enough to reproduce the two solar mass constraint of a neutron star. So from that insight, we can go back and forth, and we can try playing with the different degrees of freedom within our model and see whether it can reproduce the two solar mass constraint of the neutron star. So far, this was the bridge between macrophysics and microphysics. Like we have equation of state from the microphysics side, and we have a mass and radius from the macrophysics side. And without actually going to the star, or by experimentally measuring the mass and radius, we can anticipate from the theory itself. So we can learn from the experiments, we can learn from the constraint given by the experiment, and by doing some reverse engineering we can calculate the equation of state, and then we can play with that equation of state and understand, okay, how can I build my model better, build my QCD model better or CUD better, so that it describes the star physics. So from that matching the constraint, we can know more about what is the composition of a neutron star, right? Now, at the end, I would like to talk about gravitational waves, like for a couple of slides, which are also very hot topic during these days. After this gravitational event in 1787, I guess. Um, so so we have neutron stars, and we can also have neutron star mergers, right? So what is a neutron star merger? Let me play this video again. So we have two neutron stars and they are orbiting each other, and whenever they are close contact with each other they attract each other and they'll lose energy in terms of gravitational waves, and this disruptance in space time, it travels through the space and eventually we can record it on the earth. So when it interfere with earth, like we can see in this diagram, so this is highly exaggerated diagram, so you have to uh, think it carefully. Like when the gravitational waves interact with the earth, it it disturbs the space time, right? It disturbs the um, length in terms of length scale, so that the disturbance is very tiny, around 10 to power minus 18 meter, which is very less. So so the question is, how can we measure such a tiny effect? If we can measure the such a tiny deformation, we can calculate the impact of gravitational wave, and we can know a lot about the characteristic of neutron star, the source of it. So from this we can make a simulation of two neutron star merger, and we can create a plot. We can create a frequency plot or strain amplitude plot, like whenever the neutron star is in spiral phase, what kind of gravitational wave it should emit, and what kind of plot it should be when they are merging or when they are in a coalescence phase, and when they are ringing down, what kind of plot it is should be. From that simulation we get this data, and we try to get the same from the real experiment. Now there are challenges in this particular context. I will talk about that in the next slide. So before that, there is also very important parameter tidal, which is called tidal deformability uh, from this merging event. So we can see whenever the two neutron stars are orbiting each other around the center of mass, they experience a tidal force. For example, the moon experience a tidal force due to Earth, or Earth experience a tidal force due to moon. So Earth has a fluid, okay, and it so Earth has a fluid like liquid. That's why we can see the tides. And similarly, in the neutron star case, it has a matter. So whenever they are in close contact, they we can see the tidal deformability and tidal bulge. So there is a tidal lag as well because they are rotating. So from this information, tidal lag and tidal deformability, we can calculate from the general theory of relativity, we can calculate the tidal deformability, which is linked to the compactness of a star. So by this, we can calculate the mass and radius of the star. And here on the right side, we can see the plots, mass, radius, which I have already shown you. And then we have a tidal deformability with respect to mass, and we can see from different process it is the scientists are trying to constrain it, but we can see it has a huge error band. So how can we get more precise results in future? If we have less signal to noise ratio, so whenever we are doing an experiment, we can see we have we are not just recording one source, we have like different kind of disturbance in the background. So we calculate this parameter, signal to noise ratio. If the parameter is better, it has a good number. If the signal to noise ratio is large, that means we have good signal. And also, in this gravitational event, we were only able to record the merger, the gravitational wave phase due to the inspiral phase, because the other phase is very sensitive. uh, the In order to measure this part of the gravitational wave event, we need to update our experiments. So I will talk about later in the few slides, like what are the experiments we can use to measure this. um, so we need a post merger signal to understand better what is going on here. And then we have a to constrain the equation of state at high temperature. So I would like to point out, the neutron star, when it is alone, like only neutron star, the physics of neutron star, it is effectively at T is equal to 0 MeV temperature. So the we don't care about the temperature, dynamics of temperature. But when they are merging together, then they are interacting with each other, and when they collide, they are not at zero temperature. So their temperature could range around 0 to 100 MeV. So at last, I'm gonna talk about, like, how can we measure the gravitational wave on Earth. So we have an experiment called Laser Interferometer Gravitational Wave Observatory, which is also called LIGO. So LIGO is a setup which can measure the tiny disturbance in Earth's um, um, lattice, like space-time lattice, or you can say Earth ground, when gravitational wave interacts with it, right? Now, when gravitational wave interact with it, it changes the size of the Earth. Like, how can I say? So in Michelson Morley experiment, we measure we see the interference of two light source. So what we do here is, we have a light source here which has been splitted. So one light source goes, one laser beam goes to this side, another laser beam goes to this side, and it strikes the mirror here and comes back. It strikes the mirror here and come back, and at some point here we record the interference between these two beams. If they are they have a constructive interference, we can say um, there was no effect of gravitational waves. But if there are some effects, some external effect that disturbs the behavior of interference, then we say, okay, there was a tiny, there was a effect of gravitational wave. So that is very tiny to measure, that we need a very good experiment in sensitive experiments, which are called LIGO. So currently we have two LIGOs, which is in US, LIGO Hanford and LIGO Livingston, and we have similar experiment in Italy as well as Japan, Virgo and Kagra. And LIGO India is also very promising uh, um, like candidate, which is yet to be finalized. Like the proposal is accepted, but the land where the experiment is going to build is yet to be finalized. Here in the plot I have shown the sensitivity of LIGO. So we can see it starts on 2015. The sensitivity was around 18 megaparsec, but with the with the time and the new technology, scientists are really working hard to increase the sensitivity of this experiment. And this is currently in its operation 4, run 4, and we are anticipating a large upgrade in the sensitivity. In O5, it can record the merging event very far away from the Earth. Then we can have more data, and from that data we can get constraints on tidal deformability or mass and radius that can be used to describe the nuclear equation of state. So this is a rough plot, rough diagram of the LIGO India. which is to be built in India somewhere, and it is mainly supported by Ayuka and RRCat. So at the end, I would like to summarize my talk. It has been a very long talk, but I wanted it to be very long because I wanted to clear all the doubts, or I want to cover all the topics all from the fundamental level, so that any person, whether he or she is a physicist or not, can understand. So if you have any question, you can just comment in the comment section of the YouTube. But okay, let me finish the summary slide. So heavy ion collision simulate extreme conditions similar to the early universe. We understood that in the slide where we described the reverse Big Bang, and the heavy ion collision can provide the data on the equation of state. On the other hand, macro side, we have neutron stars, which are compact star, very dense, and they have like types pulsars and magnetars. So we bridge them using TOV equation that connects the neutron star's internal structure to the macro observable, which can be measured by NICER as well as LIGO, calculating different quantities. And um, different theory, by now we have a constraint from NICER and LIGO, right? Now we can play with models and theory by varying the degrees of freedom, and can see what what equation of state can describe the mass and radius constraint better. So in the future, we are hopeful and excited that the new LIGO measurement will help us understand the post-merger signal and constrain the equation of state at high temperature. So when we have a high temperature, when we have a signal, post-merger signal like coalescence as well as ring down, we can tell better about the equation of state at high temperature, and that will be used in the nuclear physics community. And as a nuclear physicist, we are waiting heavily for the new LIGO experiment to be come down, and also the data from the NICER, so that we can explore the nuclear equation state more. So this was all about my talk today. Again, it was very long. Um, so if you find some error in my, like sometime I misquote numbers, right? So you can just drop it down in the comment section and let me know. I will fix it. And if you like this video, if it was helpful, do give a like and put a comment how this was helpful. And if you have a comment about how I can improve this, that is also very welcome. So with that, I would like to thank you all again for your attention, and good luck. Thanks.